This tutorial assumes you understand vectors, cosine, and at least know the definition of the dot product. If you don't, I've left some videos in the description you can watch to learn. Let's apply our knowledge of the dot product in a game engine. You can use any game engine you'd like. I prefer Roblox because it's simple and robust. The dot product has two forms when combined, which allow us to find the angle between two vectors. First, we need to isolate the angle theta in the second equation, and then substitute the first equation in the numerator. We'll use this equation to enable the zombie NPC to detect if the player enters its FOV of 90 degrees. Most game engines assign orientation vectors to objects inside the game world. In Roblox, every part in the workspace has a look vector which is already provided for us by the engine. The look vector of the zombie's humanoid root part is the first one we need to get. It is visualized in green. The second vector we need to find is the direction vector originating from the zombie and pointing towards the player. This one needs to be calculated in real time since the position of the player changes. We take the position of the player's root part and the zombie's root part and subtract them. This vector will have a magnitude that varies. It is visualized in blue. To make the calculations easier, we can normalize the vector so that its magnitude will be 1, but direction is preserved. This is okay because we're not worried about the magnitudes of the vectors here, just the angle between them. Now, we have our two vectors and we can calculate the dot product. We can also calculate the angle between the two vectors by taking the inverse cosine of the dot product. This value is generally given in radians, so I will convert them to degrees for visibility's sake. Since the zombie has a field of view of 90 degrees, the angle created by either the left or right bound of the zombie's vision will be half that. Thus, we need to check if the angle between our two vectors ever goes below half the FOV to activate aggro on the zombie. Now, let's see this in action. The FOV of the zombie is visualized in red, and the blue vector changes direction as I move around. On this whiteboard, we can see that the player vector changes, but the zombie look vector does not change since the zombie is standing still. Since the x and the y coordinates of the zombie's look vector are 0, we don't have to calculate those in the dot product. The only elements that matter is the z coordinates of both the player vector and the zombie's look vector. So after multiplying both of those, and then taking the inverse cosine, we get the angle. And this value has been truncated so that it fits on the whiteboard. Now, as I get closer to the zombie's FOV, we can see that the angle begins to decrease. And once I enter the FOV, it will see me and start chasing me. Unfortunately, I have no way of fighting back.